Then we demonstrate, not the FET, we demonstrate a versatile memory. We call it a versatile memory because nowadays you are using a non-volatile memory, just like a UBS flash memory. But present days flash memory, the speed is in microsecond. What we have done is we made the non-volatile memory even 10,000 faster. 10,000 faster. That I will show you how we made it. Yeah, 10,000 faster. And also low frequency, high speed, energy efficient, something like all kind of things. Yeah, I would like to show you all those things. Some is actually some is a little bit impossible, but we did it. So very interesting. This is also will be presented the coming conference in Hawaii this year, in next month. Okay. So how we made it? How do we make all the measured data are showing here? But I will describe in more details about all those data. So I will explain you a little bit detail later. So please, to be patient. Yeah. So this is the principle of how negative capacitance work. It's so simple, but it is nobody can make it. We made it. This is the basic structure of FET. This is source and the drain, and there's a channel around here, and there's just a gate to control the carrier flowing from source to drain. So how do you control the carrier under the gate? So the gate is important. And under the gate, there's one capacitor. This is a normal structure like this. This is the normal structure, this capacitor. Anyway, we put another negative capacitor in series with normal capacitance. These are very simple structures. We just put another negative capacitor to make it work. And how do this kind of structure work? I will explain you a little bit about using a very simple theory. Second theory, this phi is the real control potential to control the channel, and the outside is gate voltage. So how do we boost the outside control voltage to here? And then, if there's 1 volt and you can boost this voltage to 10 volts, then you have value controllability 10 times of the previous one. So the channel carrier can be controlled much easier by boosting up the potential from here to here. Therefore, because of negative capacitance, it's rarely the voltage can boost to here 10 times, more than 10 times. And there's a simple equation to describe this one, because this two capacitors in series. Therefore, the surface potential is expressed in this way. And this is in series. The negative capacitor and the normal capacitor in series. Therefore, this is very simple equations. However, because this is a negative capacitance, therefore, if a negative capacitance, the negative capacitance is close to the positive capacitance, this term can become 0. So the voltage could be infinity. So this is a very tremendous amplification by using a negative capacitor. This is a simple equation describe this one. Therefore, the issue is how to make a real negative capacitor. Nobody can do it. We made it, and this is simple plot to indicate how the outside external get potential can boost to even bigger, even larger for the control surface potential. This is a very simple plot to explain how we do this one, this kind of boosting, potential boosting actions. And the important thing is that we need to make a negative capacitance. Therefore, polarization is important. And later I will show you how we make this kind of polarization from quantum mechanics, from first principle, how do we make it, and from material science, how to make it. I will explain later. But I would say, if there's a polarization curve like this electric field, the polarization, you can really make this kind of curve, then there is a possibility to have this kind of negative capacitance, because dP, dE, this is negative. So we can make a negative capacitance if we can make this kind of hysteresis, polarization. The issue is how to make a polarization curve like this. That's the key issue. So importantly, we are using so-called strain gate engineering. Strain gate engineering. We put a tantalum nitride on top of ferroelectric materials. Then the strain develop under. Therefore, using this kind of strain, we can make this kind of hysteresis. This diagram shows how to make all those things step by steps. And this is how the strain work for crystallization. Conventionally, we deposit this kind of materials, hafnium oxide. However, hafnium oxide conventionally is kind of a monoclinic crystal structures. Important is that how do we make orthorhombic is important. How to transform from monolithic crystal structure to orthorhombic structure. That's important. The answer is by using strain. By using strain, we put tantalum nitride on top of hafnium oxide, then they induce a strain and induce a correct crystallization structures. So this is a kind of strain engineering is key to make orthorhombic crystal phase. That's important. So the key is how to make this. So we use strain engineering. This is also the first time we use this principle to realize the right crystal structure like this. And this is another. This is the kind of energy versus strain, and the energy versus strain. You can produce a pertinent strain here, then you can produce a good crystal structure here. This is theoretically by material science principle. You can do it. So this theoretically, and how we make it, and this is we're using first principle quantum mechanically to calculate the tensile state, and then because of the strain, the tensile state is really from very almost nothing to very high density. Therefore, produce electron concentration is also the key to make a polarization. So this kind of theoretical prediction is really proved by our experiment. So we made it. Let me see. By using this kind of two principles, we really made this kind of structures. This is a common oxide. There's no ferroelectric, but we put a hafnium zinc oxide, and we put a tantalum nitride gate, then produce a strain force on those materials, and they really produce electron concentration and produce a polarization. And this kind of structure, this kind of curve, is really demonstrates that the polarization is produced instead of this one. If there is no strain, no polarization, it's only this curve. But by using, by applying a strain, that there is a strain and the polarization produced, a very large polarization produced, and it was verified experimentally by just experimental result. Nevertheless, it's very important that the substrate strain is very important for energy saving. In the present day, the substrate strain is almost 100 or 200, and the theoretical value is 60 millivolts per decade. We are making a value is lower than the theoretical limit. We are below 60 millivolts per decade. It's already demonstrated. So that's also important to have a very good energy efficient for this kind of device. Not only for large device, but also for the good small device. Like TSMC, they're working on 3 nanometers. They need this kind of sign to help them to make the next generation device in the circuit, VSI, something like that. So this is another energy. I think this was presented previous slide. The energy and the polarization curve. This is the regime of a negative capacitance. How do we make this kind of experimental curve is also critical. It's very important. So we do make negative capacitance in those regions. So that's an important thing to prove that we really made a negative capacitance. The only one in the world we made it. Although the principle very very simple. Then we there are also presented this kind of thing. Energy efficient. So we presented, although it's a p channel, we presented is already below the theoretical limit. We presented this to maybe to 50 millivolts per decade. This is already presented. And this energy polarization curve, as I presented previous work. And this, because this is kind of flash memory, and we need make it very fast. The present flash memory, the speed in microsecond, and our present work can make in nanosecond. Therefore, the speed is 1,000 times faster. And this curve really demonstrates this nanosecond pulse. We can make it nanosecond. I can explain that. If you want to download a movie, 15 minutes movie, by using, not a whole, like a gun with the wind, the movie, but download a movie, a long, maybe 4 hours movie to this flash memory, it takes you 15 minutes. But if you using our this flash non-volatile memory, you can download less than 1 second. Less than 1 second. That's possible. Yeah. So this is very fast non-volatile memory we can make in the future. And there is 2 phases. It's the antiferro and antiferro and ferro phase. In antiferro, the window is depend on with antiferro phase or ferro phase. So this is the antiferro and the ferro phase. So window is also depend on the phase. This is we have demonstrated. However, with a ferro phase, the speed much even faster, but the window is smaller. But using this antiferro, the speed is very fast. Well, a little bit slow, 20 nanoseconds. However, there is still much faster than present days non-volatile memories. So all those things we have already demonstrated. So very interesting. And this figure shows that the substrate shrink also depend on antiferro or ferroelectric phase also. Not only a threshold voltage, but also the substrate shrink. Depend on the phase. Okay. And this also demonstrated the speed. Yeah, the speed. Yeah, in nanosecond speed. And also demonstrate the window, the memory window. Because larger memory window, it can store more memory. It can multi-level, so it can therefore open up a very large window. This is almost a 2.5 volts window, so it's still very large window can be. This is a real expander result. So it also demonstrates a very large memory window we can achieve. Yeah, so very interesting. So, but also interesting that the drain voltage is very small, only 0.2. Present day TSMC device, a circuit, they are working at 0.8 volts. And we are working, we can beautifully perform at the 0.2 volt. What means that? 0.8 divided by 0.2 is 8 times. 8 times the square is 64 times. That means energy consumption is 64 times less than present day's FinFET, 64 times. So that I have demonstrated the equation before. So previously, you can see how the energy saving can we make. So it's very exciting about that. Very interesting. Yeah. This is another chip, really 5 nanosecond or 10 nanosecond, really working very fast. And this is a lifetime. We can demonstrate that the lifetime with the on and off on-off ratio is 1 million times on and off ratios, and you can on and off for more than 10 to 16 at the temperature of 85. That means the memory can sustain infinity. For infinity. Don't die out. No, don't die out. So this is another interesting we have demonstrated. Even at the temperature of 85